Morning, guys. I'm just a bit slightly pissed off because I just went through and made a 40-minute video, and um, my iPad decided to change the recording. So instead of recording sound, it didn't record it. So the video that I made, which was absolutely fantastic, even if I do admit myself, uh, it didn't have any sound, so it was kind of pointless. Um, yeah, I don't know how to get rid of that. Wonder if I can. Doesn't really matter. Okay, so obviously I'm not there today because I'm not feeling well. Um, Alright, we're looking at the area between two curves. So some of you might have done this in methods. The main difference is with Spesh is that we do it between curves in relation to the y-axis as well. But basically what you want to do, if you want to find the area between two curves, you need to find either where the curves intersect or they need to be bound by some values. So in this case here, in this graph, the curve would be bound by A and B. It would need to be split into two regions because if you have a look here, this graph, if I find the area under the graph of g of x, I'm going to get this whole area here. And then if I find the area under the curve of f of x, I'm going to get this area here. And if I want to find the area between the two, I do the area under, so if I want from A to C, the area under g of x minus the area under f of x, that gives me the area between the two, which is this purple here area that we're left with. So that's that bit there, g of x minus f of x. And what you will notice over here is that they swap and f of x becomes higher than g of x. So in this case here, I've got to do the area from f of x, which would be this purple area under here, minus the area under g of x, which would be this green area, and then that will give me the area that's in between them, which is here. So in this case, we would use the boundary C to B, f of x minus g of x dx, and that would give us the two areas between those outside bounds, so A to C, and then, and then from C to B. Okay. Similarly for the y-axis, if we want to find the area between two curves, we know if we wanted to find the area under g of y in this case, we would integrate from A to B, so it would give us that whole area. And then we would find the area under f of y from A to B. And if we do the area under g of y minus the area under f of y, we would get the area between the two curves. I've said in each case above, it's always the graph for the function furthest away from the x-axis, x or y-axis, subtracting the function closest to the x-axis over the interval. Also, sometimes you might not be able to integrate a function with respect to x. However, you can do it with respect to y, so you might want to change it. That's not right, what I've said here. It's always the graph that's highest. So highest minus the lowest. So in this case here, if I had two sketches, the one that's furthest away is the highest on the lowest, but if I had it with something like this and that, it's the highest, which is the green, minus the lowest, which is the blue, and then I'll give you the area in between. So it's not the one that's furthest away, it's the highest value on the domain minus the lowest. If it's in terms of the y-axis, it's the one that's higher, which is to the right, minus the one that's lower, which is to the left. That'll give you the area in between. You might say, why is that the case, even if it's below? If I had a function like, let's say, there's one function, there's another function. If we know the area under the, I should make them different colors so you can distinguish. So let's say f of x, and there's a to b, and then we'll call the other one g of x. Now, if we go by what I said before, it's always the higher function. So the integral of a to b, f of x, minus g of x dx. How can that be right, you say? Well, if I found the area under f of x, it could be something like that area is -6. Then if I found the area under g of x, that area is -8. If I subtract that, -6 minus -8, that becomes +2, which is this area in here, that region shaded in there. Okay, so it's always the higher one, the higher y values, minus the lower y values on a domain. Okay, we can get rid of that now. And you've also, sometimes you have to find where they intersect. So, sorry about the sniffing, but I just can't help it. Okay, x squared minus 2, so that's going to go through -2. It's going to look like something like that. Really bad graph, but okay. And then I've got 2x plus 1, so there's 1. It's got a gradient of 2x. So we obviously want this area here because it's bounded by the curves. It doesn't say anything about axes, just the curves. So the first thing we need to do is to find where it intersects. We know, let's call the straight line f of x. So f of x is 2x plus 1. G of x is x squared minus 2. Let's find where they intersect. So 2x plus 1 equals x squared minus 2. Bring it all to one side. 0 equals x squared minus 2x minus 3. The good thing is on the first time I did this, I stuffed that up. I couldn't add, and I ended up with a -1. But now we got it right. So if I factorize that, x plus 1, x minus 3, so x equals -1 or 3. So obviously this point here is -1, this point here is 3. Okay, now we've got to use what I said before, -1 to 3. My higher function, which is f of x, 2x plus 1, minus my lower function. Make sure you put a bracket around it because there's more than one term. You should always put a bracket around it anyway, so you don't stuff it up. I get the integral from -1 to 3, (x squared plus 2x, 1 minus -2 is +3 dx. Okay, now we just got to evaluate it. So (x cubed on 3 minus x squared plus 3 between -1 and 3. If we put 3 into that, you get -27 on 9 on 3, which is -9, minus 9. Should that be a minus or a plus? That's a plus. So that'll be a +9. Because when I integrate that, I get plus. Okay, so +9 and then 3. Oh, when I integrated that, I forgot my x. 3x, so I get +9. So I get -9 plus 9 plus 9. Minus, when we put -1 into that, -1 cubed is -1 times -1 is 1/3. -1 squared is +1. Minus 3. That's going to give us 9 minus, okay, I've got 1/3 plus 3/3, -1/3, sorry, plus 3/3 minus 9/3. So, minus 1/3 plus 3/3 is 2/3. I'm going to get minus 7/3, which is 9. It's going to be 10 and 2/3 square units. because I've got 9 plus 1 2/3. Of course, we can check it on the cas. So -1 to 3. Okay. -1 to 3 minus x squared. Can't remember what it was. Plus 2x plus 3 dx. 32 on 3, which is 10 2/3. Hooray, we got it right. Okay, find the area of the region bounded by the curves x squared plus 1, 4 minus x squared plus 1. So there's x squared plus 1. Let's call it f of x. Okay, g of x, we're going to call that 4 minus x squared. There's 4. G of x. F of x, we know, is below the curve. We want it between -1 and 1. Now, -1, does it occur out here or does it occur inside here? Well, that's something we've got to find out. So let's find out where they intersect. Because if they intersect outside -1, then we just need to find it from -1 to 1. But if they intersect inside -1, we're going to have to split it up into 3 regions. We're going to have this region, then we'll have that region, and then we'll have that region, and we'll end up with like a lolly wrapper. But I know what the answer is, but let's work it out. So I've got 4 minus x squared is equal to x squared minus 1. Now let's bring it all to one side. 2x squared minus, is that right? X squared plus 1, 4 minus x squared. Okay, x squared plus 1. Okay, so I'm going to get 2x squared minus 3 equals 0. We get x squared is equal to 3 on 2. So then we get x equals plus or minus root 3 on 2. Now, is root 3 on 2 greater than 1 or less than 1? Well, we know root 1 is equal to 1. So root something greater than 1, that has to be greater than 1. So we know that these intersection points, they're going to be greater than 1 and -1. So we can just integrate from -1 to 1. Or, because this thing is symmetrical, we can be super lazy. Actually, it's just super smart, I would say. We can just integrate from 0 to 1 and times it by 2. Okay, so let's go. The area between the curves is 2 times 0 to 1. My higher graph, 4 minus x squared, minus my lower graph, x squared plus 1. dx, 2. Okay, I've got 4 minus 1, which is 3. Minus x squared, which is minus 2x squared, between 1 and 0. 2, when we... Oops. I stuffed that up. I didn't integrate. Okay, 0 to 1, 3 minus 2x squared dx, which is 2. 3x minus 2x cubed on 3, between 1 and 0. Okay, we've got 2. When I sub 1 in, I get 3 minus 2/3 minus 0. 3 minus 2/3 is... What is 3 minus 2/3? That's 2 1/3, which is 7/3. We don't need to put... Well, we know that that's just going to be 0. So I've got 2 times 7/3, which is 14/3 square units. Or we could say, how many 3's go into that? 4 and 2/3 square units. So that's what the area is between the two. We can go and check it. I have got between, we'll go from -1 to 1. Our higher curve was 4 minus x squared, minus our lower curve, which was x squared plus 1 dx. 14 on 3. Looks like we got it correct. Okay, this next curve here, find the area of the region enclosed by the graphs. Okay, so in this case here we need to quickly give it a sketch. I know that g of x equals x, so that's it, that line there. And the other curve is x cubed, so x cubed looks something like that. Okay, so this is g of x, this is f of x. Once again we can use symmetry. So here and here, we've got to find where they intersect first. So x cubed equals x cubed minus x equals 0, x squared minus 1 equals 0, x plus 1, x minus 1 equals 0, so x equals 0, -1, 1. Which graph is higher on the domain? Well, g of x minus f of x, and of course this value here is 0, this value here is 1. So let's integrate between 0 and 1, g of x minus f of x, and times it by 2. So area, what just happened then? Sorry, I hope I don't make you dizzy. 0, 1, 2 times my higher graph, x minus x cubed dx. 2, I get x squared on 2 when I integrate, minus x to the 4 on 4, between 1 and 0. The reason I try and use 0 is because when you sub it into a polynomial, it just disappears, like it's 0. Okay, so I get 2 times, when I put 1 into that, I get a half, minus 1/4, minus 0. Of course, that's 0. A half minus a quarter is a quarter. So I get 2 times a quarter, which is a half, square unit. So that is the area between there and there, my two blue areas. Once again, we can check it. We can integrate from 0 to 1, x minus x cubed dx. That gives us a quarter. We've got to times it by 2. So 2 times my answer. I get a half. The other thing you can do if you want to find the area between two curves, you can always do the lower bound, the upper bound, and then the modulus of x cubed minus x dx. So as long as, it doesn't matter, we can do x minus x cubed or x minus x cubed, it'll still give you the right answer. So as long as you've got your endpoints and you find the modulus of one function minus the other, it'll always give you the positive area between the two. Oh, I'll just close my program. So we can check it for this graph here, just to make sure I'm not lying. So -1 to 1, x squared plus 1. Integral -1 to 1. Now, modulus x squared plus 1 minus, now my other graph was 4 minus x squared dx, and we get 14 on 3. If we did the same thing, but this time I did 4 minus x squared minus x squared plus 1, it's 14 on 3. So it doesn't matter which order you put it, as long as it's one minus the other, and it's in between the two endpoints, it'll give you the correct answer. Okay, lastly, find the area of the shaded region of between those two things. I'm just trying to work out how do I get rid of that shape. I've done it before, but I can't be bothered trying to work it out. Okay, so we've got to find this area. We know that that's pi on 4, because we know sine of pi on 4 and cos of pi on 4 are both 1 on root 2. We know that that's 5 pi on 4, because cos of 5 pi on 4 and sine of 5 pi on 4 are both negative 1 on root 2. The higher graph in this case is sine x. So f of x is sine x. G of x is cos x. We want to integrate from pi on 4 to 5 pi on 4. Now, because we're doing it without modulus, we need to make sure we've got the correct one at the top. So sine x minus cos x dx. Okay, when we integrate, was that right? Sine x, yeah, minus cos x. When we integrate sine x, we get negative cos x. When we integrate cos x, we get sine x, so negative sine x, because there's already a negative there. Pi on 4 to 5 pi on 4. Okay, when we evaluate it, we're going to get negative cos of pi on 4. Cos of pi on 4 is 1 on root 2, so negative 1 on root 2. Sine of pi on 4 is 1 on root 2, so negative 1 on root 2. Minus cos of 5 pi on 4 is negative 1 on root 2, so negative 1 on root 2. That's right. And then, is that right? Negative cos of 5 pi on 4. Cos of 5 pi on 4 is negative. So I'm going to get negative. When I integrate cos, I get sine. Sine draws to, yep, okay. I've got the terminals around the wrong way. Pi on 4, 5 pi on 4, because this will make more sense now. I'm like, it's going to end up being 0, which it's not. Okay, let's put 5 pi on 4 in. So we get negative times negative 1 on root 2, because cos of 5 pi on 4 is negative because it's in the third quadrant. So negative 1 times negative 1 on root 2 minus sine of 5 pi on 4 is also negative, so negative 1 on root 2 minus cos of pi on 4 is 1 on root 2 minus sine of pi on 4, which is 1 on root 2. Okay, here, there, negative 1 times 1 on root 2 is 1 on root 2, but I'm going to make it root 2 on 2. That's going to be plus root 2 on 2 minus root 2 on 2 minus root 2 on 2. Oops. Okay, so here root 2 on 2 plus root 2 on 2 is just root 2. Negative root 2 on 2 minus root 2 on 2 is negative root 2. So I've got minus root 2, which is root 2 plus root 2 is 2 root 2 square units. So the area between those two curves is 2 root 2 square units, so we can just check it, because I seem to have made a lot of stuff ups in that one. Okay, so we go from pi on 4. Oh, don't forget, if you want to find out where they intersect, you can always use your cas. Sine x equals, no, it's not equals cos of x. Solve, and we want it between 0 and 2 pi. More solutions may exist. Oh, it doesn't give it as an exact. I would then delete this and then put outside given 0 is less than x, which is less than 2 pi. Okay, so pi on 4, 5 pi on 4. And then, of course, we integrate from pi on 4 to 5 pi on 4 sine x minus cos x dx, and we get 2 root 2. So we know that it's correct. Cool. Alright, I think I have explained everything. I told you about the curve. So it's always the higher curve minus the lower curve. It doesn't matter if they go above and below the axis. So what I mean by that is you can see here some of this is below the axis, some of it's above the x-axis. It's just the higher curve minus the lower curve. Because if you get a negative area, when you do one subtract the other, it'll end up making it positive, which is a nice little thing to happen, because then you don't have to worry about positives and negatives. Okay, good luck with that. Good luck at the senior dance or the Year 12 formal tonight. Sorry I can't be there, but one, I forgot about it, so I didn't even put my name down to go, because teachers have to put their name down early and I missed out. And two, I'm crook anyway, so I probably would have pulled the pin. But I hope you guys have a good night. Don't miss me too much. Yeah, I will definitely try and be at your end of year graduation, whatever they call that. Okay, have a good night. See you not Monday because we have assembly. Hopefully I'll try and make another podcast for that. All right, bye.